Joe asked for a little information on the kinematic motion equations of a bicycle, and this is because Greg wrote a really nice piece on aerodynamic resistance on the bicycle. The only thing wrong with that piece is that it said 5% was the total for rolling resistance and everything else, and that's just nowhere near accurate. So the simple way to look at this is to develop the force equations on a bicycle. One of them is rolling resistance, another was air drag, and the other is riding up hills or down hills. Starting with rolling resistance, you find that the force is equal to some coefficient of rolling resistance times your weight, the weight of you and your bicycle. It turns out that for good tires, it's around 0.005 times your weight. In my case, it's around 1 pound of rolling resistance. Now the aerodynamic drag is, the force is 0.01 times the velocity squared. Greg mentioned velocity squared, and this is where it's at. Now, the 0.01 is a nice coefficient. It works. I measured it, and it's pretty close, and it comes out really well for me. If you're much bigger than me, it'll be a little higher. If you're a little smaller than me, it's a little lower. If you're on aero bars, it'll be a little lower. If you sit up very upright, it'll be a little higher. But 0.01 times velocity squared. So if we're going 10 miles per hour, 10 squared is 100, times 0.01 is 1 pound. So at 10 miles an hour, we get 2 pounds of force resisting our forward progress. Think of that as force against the rear tire. You have to push that tire with 2 pounds of force to move forward. Half of that force is coming from rolling resistance and half from aerodynamic drag. Now you want to look at power. Force times distance is work. Work per unit time is power. Distance over time is velocity, so force times velocity is also power. Now, we had 2 pounds of force. We're going 10 miles per hour. The power is 20 pounds miles per hour. Now, pound miles per hour doesn't sound very familiar to anybody since I invented it, but it's truly a measure of power. Pounds are a measure of force, not of mass. And miles per hour is a measure of velocity. So pound miles per hour is a very real measure of power. And the thing is, they're things we're used to. I think in pounds, I think in miles per hour. I don't think in meters per second or newtons. So 2 watts happens to be equal to a pound mile per hour. So 20 pound mile per hour is equal to 40 watts. Wind. Drag is proportionate to the airspeed your body is passing through. So you've got to add your ground speed and the headwind that's hitting you. So we go back to our force equation and we see the coefficient of rolling resistance times weight plus 0.01 times velocity plus headwind squared. Now if we look at the power equation, again it's force times velocity. I've written the force equation in brackets and then multiplied that by velocity or ground velocity because I don't want you to the mistake of going velocity plus wind cubed. It's not. It's velocity plus wind squared. That's the drag. Power is found by multiplying the force times the ground velocity. People make that mistake. I've seen it in magazines. I've corrected the guy. He said he got it out of MIT's book, Bicycling Science, and he copied it wrong. Now, when we talk about headwinds, suppose you're standing on the road, you're looking down the road, the wind's coming from a 30-degree angle at 10 miles an hour, like this red arrow. Well, you can break that into 2 components. And the component coming straight at you is equal to the cosine of 30, 0.866, times the speed of the wind. If it's 10 miles an hour, that's going to be 8.66 miles per hour wind at your head. And that's what you're going to add to your ground velocity when you do the equation. So let's look at this for a force equation at 10 mile headwind, 10 mile an hour ground speed. We get 1, the rolling resistance, plus the magic number 0.01 times 10 plus 10 squared, or 20 squared is 400, times 0.01 is 4. And so we have 1 pound of force from rolling resistance, 4 pounds from air resistance. The rolling resistance is now 20% of the total effort or resistance. The power is the force times the ground velocity, so 5 pounds times 10 miles per hour is 50 pound miles per hour, or 100 watts. Now let's look at 20 miles per hour. We find we get similar forces when we have no wind. We have 1 pound of rolling resistance. We got 0.01 times 20 squared, or 1 plus 4 equals 5. 5 times 20 now for power. We get 100 pound miles per hour, or 200 watts. And that's really just about right. I just did a bunch of tests up and down the road, both directions, a little bit of headwind in one case. I averaged 19.8 miles per hour and averaged 210 watts. If the headwind hadn't been there, I'd been closer to 200 watts at 20 miles per hour. So that's really a pretty close measurement. Let's take a closer look at the wind term. 0.01 times velocity plus headwind squared. But that 0.01 is really hiding a lot. If you look in Wikipedia, you're going to find something that looks like 1/2 rho. I've used a P for rho here. A CD V plus W squared. If the wind term is not there, it'll be 1/2 rho A CD V squared. It's kind of a mess. And then there's that V squared. It's just not intuitive. We're used to momentum, we're used to force, we're not used to V squared. There isn't any intuitive experience of V squared. But let's see if we can find it. We want a force, so let's start with force equals mass times acceleration. Acceleration is velocity per unit time, the change in velocity, so it breaks down into distance over t squared. But what is the mass of air? We've got this m, we have to figure out what that is. Well, if you think of your body going through a tunnel that's exactly the shape of your body, then the frontal air of your body is pushing all the air out of that tunnel. It's pushing this out of the way. It has to move. And air has mass. Hard to figure out what it is. You can't see it. You can't weigh it. But you're pushing it all out of the way. The length of the tunnel is the distance you travel in a period of time. If you're going 10 miles per hour, you'll go 10 miles in an hour. That's how much air you're pushing out of the way. So now, if we multiply your frontal area times the distance, we'll get a volume of air. It still doesn't give us mass. We need to know the density of the air. We multiply the density of the air times the volume, we'll get mass. So mass is equal to the area of your frontal area of the body times the distance you travel at some given time times the density of the air. So we can now rewrite our force equation putting density, rho, times A times distance, and then we have the distance over tt from the acceleration term, and that becomes rho times A times d over t, which is rho times A times v squared. That's where it comes from. Now we're still missing a 1/2 and a CD, and CD is just a number. You can cram the 1/2 in there if you want to. CD is a shaping parameter. If you're a blunt object, stalls the air in front of it. If you're sitting up on your bike, the air hits your chest, it compresses against your chest, it sort of stalls there, builds up pressure, and then it shoots out to the side, creates a lot of turbulence, and actually pushes a lot of air that's outside your tunnel of air. Air you shouldn't have had to move is now getting moved, and that's got mass. So more air mass is being moved. Then the turbulence comes around my back. I'm not very thick, and all of a sudden there's these vortices behind you, and they're creating vacuums and pulling back against you. Now if you have streamliner, it kind of points the way through the air. It moves only a little bit of air. It doesn't move any air outside of your little tunnel. And it goes around behind you, closes in behind you, and it leaves it clean, no turbulence. So that's CD. Where's the 1/2 come from? Well, if you start with energy, you can divide by d to get force. Energy is equal to 1/2 mv squared, and you end up with 1/2 md over t squared, pretty much where we started from, but you've got the 1/2 term. So if that's the way you like it, you can do it that way. With $12 worth of plastic, a little bit of mathematics to figure out how to cut it, some zip ties, some aluminum, some PVC. You can put a nose cone on your bike, sit in a nice, comfortable, easy chair, and have less than 1/3 of the drag of riding a regular road bike while you're in this comfortable chair and not on this hard seat. You can ignore headwinds, and you can cruise along at 22 miles an hour all day long. It's a pretty good way to go. Hills. There's a nice little diagram here that shows you kind of the slope of the hill, and the gravity, your weight goes straight down. You break that into components, and the component that's parallel with the slope is sort of the resistance that you're going to feel at the back wheel. You just measure the slope. It doesn't matter if you use a sine slope or a tangent slope. They're very close at small angles. And so if you have a slope of 5%, which is like the hill by Messengers or the hill on Salina Road that goes up between the trees after the creek on the way home, times 200 pounds, you have 10 pounds of resistance. Okay, now if you solve the equations for 10 miles per hour and you go to the force equation, we have CRR times W and slope times W, very similar. And then we have 1/2 P A rho A C D V squared, which we know all comes down to 0.01 times 10 squared. And the 0.005 and 0.05 could be added together and multiplied times 200, however you want to do it. The force equation comes down to 1 plus 10 pounds plus 1 pound from aerodynamic, because you're only going 10 miles an hour. So that's 12 pounds times 10 miles an hour, 120 pound-mile per hour, and 240 watts. Now with a 10% slope, you have 20 pounds of resistance. Why can't you go as fast? I can move 20 pounds, I can move 10 pounds, no big deal. And that's because power, not force, is a limiting factor. Power depends on how much ATP you can produce. So you can go up a 5% slope at 10 miles per hour, or a 10% slope at 5 miles per hour with a 240 watt bank account. So now what you need to do is you switch from physics to biochemistry and find out how to get your mitochondria to produce more ATP. That's the next challenge.